Hello, everyone. Good afternoon. I'm having some issues with Word today, and I was trying to move some things. That's why I'm a minute or two late. You don't need to hear about that rant, though. Let's go ahead and continue where we left off in 5.2. I'm just going to very quickly abbreviate some of what we've gone over. I chose that word specifically. We learned of our 6 primary trig functions that we will be talking about all semester long: sine, cosine, tangent, cosecant, secant, and cotangent. We learned that there is a relationship between sine and cosecant, cosine and secant, tangent and cotangent, and that those are each reciprocals of one another. We said that we have got to spend time memorizing which is which, because it's very easy to get that relationship backwards with a couple. Like you might think sine and secant are flips, aka reciprocals of each other, but it's really sine and cosecant. We gave their definitions in relation to opposite, hypotenuse, and adjacent, the 3 sides, the names that we give the 3 sides of a right triangle. Where our angle is here, that makes this side the opposite. If I were to put the angle on the top, then the adjacent would be instead labeled the opposite. We gave you SOHCAHTOA to help you remember the first 3. We said there's not really a great one for the other 3, but most people just use those reciprocal relationships to get them. And if you don't, if you remember that it's hype over opposite, things like that, that's fine. SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. You're going to hear me say it 50 million times. We did some examples, and we were just discussing how these are just numbers. The sine of an angle is just a number. What kind of number? It's typically a fraction, and it's a ratio of 2 of those 3 sides. Now, I say typically a fraction because sometimes the fraction reduces to a whole number, like this one right here, or a whole, or a non-rational number like this. We labeled the reciprocal relations. We labeled the fractional relations between tangent, cotangent versus sine and cosine. So the ratios of them, if you will. We proved one of them. We said you could do the proofs of any of the other things that way. We established, or hopefully reestablished, the Pythagorean Theorem. We did a couple examples, finding missing sides, whether they were a hypotenuse or a leg, which the algebra works a little differently for legs, but nothing you shouldn't have done before. We established the 3 Pythagorean identities. We said that this first one basically comes from a squared plus b squared equals c squared. The other 2 come from the first one by dividing by sine squared or cosine squared. We even did the proofs of the second and third one in that regard. The last thing we did was we talked about cofunctions. Now, admittedly, this isn't something that we discuss too much moving forward in this course, but it is still an important concept, especially when you're dealing with anything physics related. The problem might start out referencing this angle, but it's just easier to use this angle. So we can switch angles if we wanted to, and then the trig functions just have these relationships, because essentially you're swapping what you're calling an opposite and an adjacent. So something that's an opposite as a sine is an adjacent in the other version. So it's, if you do 90 minus that angle, now it's the opposite again. So sine and cosine have this relationship. The sine of one angle is the cosine of the other inside of a right triangle. The tangent of one angle is the cotangent of the other. The secant of one angle is the cosecant of the other. The blue versions are just rewritten versions of the black form here. It's the same idea, though. The cosine of one angle is the sine of the other. The cotangent of one angle is the tangent of the other. And that is where we stopped. That is where we left off. So we were at example 3. Find a cofunction with an identical value. Do not find the value. So for A, we're going to have the sine of 26 degrees. We right now do not know how to find the sine of 26 degrees. I haven't taught you how to do that yet. It's coming. Maybe not for 26 degrees. Spoilers, that's a calculator problem. But if it was something like 30 or 45 or 60, we're going to be discussing that very soon. So for now, we don't know what we're doing with this, excuse me, because all we've been taught so far is to use these triangles and use opposites over hypotenuses or adjacents over hypotenuse, things like that. That's all we've done so far. So again, we don't know how to find this. We're just going to find an appropriate cofunction that would spit out the exact same answer. Sine and cosine are cofunctions, so that means we need to switch this to a cosine. So it'd be the cosine of 90 degrees minus 26 degrees. See, it's cosine of 90 minus the other. Because if this is 26, the other has to be 90 minus 26. And the sine of this angle is the same as the cosine of this angle. That's the idea. 90 minus 26 is, of course, 64. Sorry, I was looking at something else. So that would be the cosine of 64 degrees. And that's all I'm asking for now. B. Let's do the cotangent of 81 degrees. So cotangent and tangent are cofunctions. So the cotangent of one would be the tangent of another, the other being the 90 minus the original angle. 90 minus 81 is 9. So the cotangent of 81 degrees would be the
Mr. Beckner, you're not sharing the screen. We can't see what.
I wish someone had said that sooner. I thought I hit the button.
Sorry.
Thank you very much. Better. Thank you for popping in and saying that.
Thank you.
And you know what? I do see 6 things in chat. Usually that pops up, and technology woes. All right, deep sigh, Goose Rabach, we laugh at it, haha. All right, so the good thing is all of those things I was saying earlier for the most part were just me scrolling through the old notes. So I'm gonna very quickly do that again. We discussed the 6 basic definitions, how they relate to opposites, hypotenuses, and adjacents, how sine is a reciprocal of cosecant, etc. We discussed SOHCAHTOA to help us remember the first 3. We discussed the idea of using reciprocals to remember the other 3, but we said it's an option. You can still use opposites, hypotenuses, and adjacents. There's just no mnemonic device for it. We did examples with this. Then we introduced the Pythagorean Theorem and did examples with that. Our reciprocal identities, some proofs, Pythagorean Theorem, examples. Pythagorean identities, we said that these 2 came from the first one by doing the stuff we did in class with the red and the blue ink, dividing by sine squared or cosine squared. I said this is a very helpful technique. This is exactly what your teacher does in his head to get these 2 every single time, in fact. Then we went over the cofunctions. So sine of one angle is the cosine of the other angle for a right triangle. The tangent of one angle is the cotangent of the other angle in a right triangle. Secant of one angle is the cosecant of another angle in a right triangle. Now we're doing find a cofunction with an identical value, and I am going to start that from scratch. No, erase, not grab. Erase, not grab, please. Please, thank you. Go. All right, so reinventing the wheel. Thank you for getting my attention. I don't know why the chat wasn't popping up on my screen. It usually does. All right, so the sine of 26 degrees. We said the cofunction of sine is cosine. This just puts us on the opposite angle in a right triangle. So this would be the cosine of 90 degrees minus 26 degrees. We said 90 minus 26 is going to be 64. So that would be the equivalent of cosine of 64 degrees. And I said, we're not going to figure out this yet. We'll do some of that in the next example, though. Spoilers, with a calculator. Then the cotangent of 81 degrees. Its cofunction is tangent. So the cotangent of this angle would be the tangent of this angle. So let's switch that to tangent, but we have to do 90 degrees minus 81 degrees, which is 9 degrees. So the cotangent of 81 degrees is the tangent of 90 degrees. And we will actually show these in a calculator that they are the same after the example. Third and last example of this, let's do the secant of pi over 6. I'm really glad y'all got me before this one, because this one's in radians. So secant and cosecant are cofunctions. So the secant of one angle is the cosecant of another. Remember, these are not reciprocal relations. These are going to a different angle relations. So this would be cosecant of, and I don't want to do 90 degrees minus pi over 6 since that's in radians. Now, one option is you could convert your pi over 6 to degrees, which spoilers would be 30 degrees. 90 minus 30 is 60. But if you write cosecant of 60 degrees in my math lab, it's probably going to mark it wrong. If the original problem's in radians, it probably wants the answer in radians. So I verbally went over how to convert everything. Not how to convert, you multiply by 180 degrees over pi, and that's how you get your 30 degrees. But let's actually do the radian math. So 90 degrees is pi over 2. 180 degrees is pi, so 90 is pi over 2, minus the original argument of pi over 6. So to the side, you got to do pi over 2 minus pi over 6. You got to get an LCD between a half and a sixth, basically. So pi over 2 minus pi over 6. The LCD between 2 and 6 is 6. So we're going to change those denominators to 6's. For the first one, 2 will go into 6 3 times. 3 times pi is 3 pi. For the second one, 6 goes into 6 once. 1 times pi is pi. 3 pi minus 1 pi is 2 pi. Remember, there's an implied 1 here that we normally don't write. You're free to in your work, but I don't like keeping it there because it's bad for answers. So pi over 2 turned into 3 pi over 6. If you're rusty with LCDs, I've already told you, you can't be rusty. You've got to derust. But then 2 and 6 will reduce to a 1 and a 3. Those are kind of ugly, 2's and 6's. 2 pi over 6. 2 and 6 reduce to a 1 and a 3. So that becomes pi over 3. So this subtraction is pi over 3. So the answer would be cosecant of pi over 3. Now, pi over 3 is actually 60 degrees, and that's one of the angles that we will be discussing on how to convert them. Not this moment. I said convert, I meant actually simplify. So let's pull out a calculator because we're going to need it for the next set of problems. Get my TI-83. If you have better than a TI-83, that is perfectly fine. This is kind of the bare minimum. I mean, a TI-82 will do the job, but I don't even know where you uncovered that relic of the past if you got a TI-82. There's my digital TI-83. Now remember, this is important moving forward in our class. You have to check your mode. There's a radian mode and a degree mode, because when you type these things in, so like the cosine of 64 degrees, here's my cosine button. If I do 64 and then close the parentheses, right now I get 0.3918, but if I change the mode, if I go down and make it degrees, so it was actually in radians originally, which means it was wrong. Then hit second quit to get out of that screen. So because 64 is degrees, this was calculated in radians. This is wrong, 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 wrong. Cosine of, oops. Cosine of 64 degrees. You don't have to close the parentheses for a singular argument like this, but we'll get into more complicated problems, so it's a good habit. Look at that, it's a different answer. It's 0.438, blah, 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 blah. So your answer will be dependent on the mode. If you're in degree mode, you'll get one answer. If you're in radian mode, you'll get another answer. So 64, that was a degrees, so I gotta make sure I'm in degrees. I gotta make sure, oh, the second answer was right. So let me just display the correct one. This is in degrees, 64 degrees, boom, there's the answer. How about the tangent of 9? We can hit tangent, 9. We're still in degrees, it doesn't just reset automatically. I'll check to be safe. Yep, it said degrees. And it's 0.158, blah, 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 blah. So this is the ratio of the opposite to adjacent for the tangent or the adjacent to the hypotenuse for the cosine. You don't have the actual links, but that's what they would be if you divided them out. That can be just as helpful. Whether this is a big number or a small number can be helpful. How about cosecant? I see sine, cosine, and tangent, but I don't see secant, cosecant, and cotangent up here. That's because they're not in any TI-83 or TI-84. They might be in a more advanced graphing calculator, but I'm going to assume this is what we're all working with. Cosecants are reciprocals of sines. So if I want to do the cosecant of pi over 3, here's what I do. And it's not this. You see in yellow sine raised to the -1, that looks like a reciprocal. It's actually not. That's called an inverse sine function. It is different. We will study it. So please note those yellow ones on my keyboard. It doesn't sound like quite the right term. On the calculator, kind of above the buttons, those are inverse trig functions. The way to do a cosecant, because it's the reciprocal of sine, you do 1 divided by sine. Now that says pi over 3. So to get pi, I gotta get this yellow one, so second, and then caret, divided by 3, close the parentheses, and I'm gonna hit enter, and then I'm gonna say, do you think this is right or wrong? 54.7, blah, 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 blah. Now, just looking at the number, you don't know any sense of what these should be, so that's not gonna help you. What I mean by is it right or wrong is, were you in the correct mode? So pi is a radian, but our mode's in degrees, so that's not right. So to get that final one correct, I actually got to switch back to radian mode, and I can actually use second and enter to recall the last thing I typed. It's a shortcut, so I don't have to type the whole thing again. And you can see that the answer is actually 1.15, a significantly smaller value. So those are subtle nuances that you have to pay attention to. You have to be careful with. So let's do that for example 4. We are going to evaluate in a calculator. Okay. We're going to have the sine of 26 degrees. I'll go ahead and write them all up at once since it's just type it in. For B, why did I do it equals? Because I was looking at one. The cosine of 3 pi over 11. Not a very common angle, but that's all right. For C, we're going to do the tangent of 428 degrees. And then for D, we'll do the cosecant of 45 degrees. And I'm going to warn you, in about 8 minutes, I'm going to have to go on mute for probably about 5 minutes total, maybe less. I have something to take care of on a very specific time that I can't avoid. Sorry for that. So I'll let you know, and if I can still type, I will, but I have to be talking to someone else. I'm sorry for that, but it's only going to take a few minutes. I promise. So sine of 26 degrees. Calculator. Let's clear the screen so we don't get any of that confused. Probably should check our mode first. We're in radians. Ooh, that would have been bad, right? So let's switch to degrees, hit enter. Second, quit to get out. Second mode is where quit is. Sine 26. You don't have to type the symbol because of the mode being degrees. It knows this number is a degree because it's inside of a trig function. It's not like if I type 26 or if I type pi that being in degrees or radians is going to change anything. It's when those numbers are inside of trig functions. So the answer is 0.438, and I didn't specify to the number decimals, so now I'm going to 3 decimal places. So 0.4383, we round down to 0.438. Easy as pie. Pun intended. I know, I'm terrible. Cosine of 3 pi over 11. So if I just do cosine 3 pi over 11, it's going to be wrong because we're in degrees. We got to go back to radians. These problems don't have to be all degrees and then all radians. They can flip-flop like this. Probably why I did it that way. Cosine 3 times pi, so second and then the exponent button, divide by 11. See, I clicked too quick, so the extra 1 didn't show up. Close the parentheses, drum roll, and rounding to the nearest thousandth, that should be 0.655, because the number after that, 4, rounds us up. See, that's an 8, so we round up to the 4 to a 5. These last two are in degrees, so I won't have to check the mode after this, but I do need to switch it back to degrees for now. second quit. Tangent of 428. So this has gone a little more than a full circle. It does have an equivalent angle, a coterminal angle, but we're not worried about it. Every angle has a coterminal angle. We get 2.475. 2.475 when rounded to the nearest thousandth, 2.475. And then cosecant of 45 degrees. Same issue we had up here with trying to do a cosecant of pi over 3 in a calculator. There's no button for it. So we need to change this first. So cosecant of 45 would be the same as 1 over sine of 45 degrees. Okay, so then we can type that into the calculator. We're still in degrees. 1 divided by sine of 45. Close the parentheses. And we get 1.414. And there we go. Right. That is 7.2. Sorry, 5.2. I told you I'm going to say that a few times. I'm still used to this being chapter 7 because it was chapter 7 for me for like 3 or 4 years, if not longer. It's chapter 6 for like a semester. That's 5.2. So we're going to save it. Hopefully Word doesn't crash opening a new file. We're going to go to 5.3. Functions of any angle. Center, enter, spacing, left, give myself some space. If I haven't said, I have to do that at the beginning so that the pen and the text really confuse each other in Word. It's a little silly. And hitting enter sometimes makes text go down. And if I don't do that, it can just break the whole page. Trig functions of any angle. Now, it's kind of funny that I'm going to say of any angle because we're primarily going to study 3 angles and extensions of them. So there are 2 very important triangles to memorize. Trig. Now, some of you may have had a trigonometry class where your teacher was very emphatic about memorizing the unit circle. And I will introduce the unit circle eventually, but you will never hear me say you need to memorize the unit circle. I strongly dislike the unit circle for my type of learning. Remember how I told you the 3 forms of the Pythagorean identities, how I only memorize 1. And I mean, I technically have the 2nd and 3rd memorized in my head at this point, but I still just always do that quick little algebra trick and canceling things to get to them. That's how my mind works. And I think a lot of people's brains work that way and they don't realize it versus just straight up memorization. So we're going to have to know things like the sine of 30, the sine of 45, the sine of 60, the sine of 90, but we're also going to need the sine of 120 and 150 and 180 and all these other angles up to 360 degrees, not just the sines, but the cosines, tangents, et cetera, et cetera, et cetera. So you'll see teachers give this giant unit circle with all these answers, 6 for each angle, and they say memorize it. No. That entire unit circle can be reproduced by memorizing 2 triangles, the quadrantal angles, and then reference angles. That's 3 things that you can put together, 2 of which are extremely simple with practice. One of is just a memorizing of 2, again, very simple triangles. And you can build the whole thing from scratch if you wanted. You don't have to spend 6 hours memorizing just a bunch of data without understanding why it's there. So what are these 2 triangles? The first one is the 45-45-90 triangle. And I've already alluded to these in a previous class. So that's 90, 45, 45. So the basic idea here is that if this is 45 degrees and this is 45 degrees, if these angles are equal, the sides have to be equal. So if, let's say, if this length was 20, this length would also have to be 20. but we're going to generalize. Let's make that number as small as possible. What's this and an easy number to use? The smallest easy number to use would be 1. So 1 and 1. That's 1, that's 1. If it's 2, that's 2. But this makes it easier. We can find the hypotenuse by doing the Pythagorean theorem. So we can find this by the Pythagorean theorem. So just really quickly below, if we take 1 squared plus 1 squared and set it equal to, let's initially call it c squared. Each 1 squared is 1, so that's 1 plus 1 c squared, which is 2 equals c squared. So you take the square root of both sides so that they cancel on the right side and just get a c, and you see that c is equal to the square root of 2. That is how we determine that side's length. The next one is going to be, and I'm going to go ahead and draw it up. We'll do the proof after I have this quick discussion with somebody. I'm going to try and do this as best as I can. That's going to erase the whole thing. Yep. I can do better than that. Drawing blind when you were already a bad artist and have terrible handwriting. There we go. So this is the 30, 60, 90. Oops. 30, not to the 6th power, 30 degrees, 60 degrees, 90 degrees. Now for reasons that I'll make you hold your breath on, the side length opposite of 30 degrees we want to be 1. The side length that is opposite the 60 degrees is going to end up being a square root of 3. And this length right here, the hypotenuse, is going to end up being a 2. So this is the 1, 2 square root of 3 versus the 1, 1 square root of 2, or the 30, 60, 90 versus 45, 45, 90. It just depends on how you want to label them. All right, so give me hopefully no more than 5 or 7 minutes. I'll be right back. Sorry for the pause. I wish I didn't have to. All right, so these are your two important triangles to memorize. We kind of rationalized how this one works. Like we said, if this is 45 degrees, this has to be 45 degrees because they add a 90. That means the lengths of the legs have to match. The best thing to do in this instance is to make them ones. And then the Pythagorean theorem showed that that was a square root of 2. I gave you this one. We said we want this to be a 1, the hypotenuse to be a 2, and this other leg to be a square root of 3. Now, what is very specific here is that the 1 is opposite the 30 degrees, and that the square root of 3 is opposite the 60 degrees. There's a relationship here. The bigger the angle, the bigger the side opposite of it. 1 is bigger than square root of 3. I just said that wrong. 1 is smaller than square root of 3, excuse me. 1 is smaller than square root of 3, so it has to be opposite the 30 degrees. Square root of 3 is bigger than 1, so it has to be opposite the 60 degrees. 2 is actually the biggest number, and if you don't trust me, we'll show you what the square root of 3 is. Square root 3, it's 1.7. So that's the middle number. And it might confuse you because you might just think it's a 3. No, it's square root of 3. So again, smaller angle gets the smaller number. Bigger angle gets the bigger number. The biggest side is the 2, and that's opposite the biggest angle of 90 degrees. I cannot tell you how many students will put the 1 over here and the square root of 3 over here with the 30 and the 60 set up like that. It's wrong. You have to memorize it. You have to practice it. You have to be careful. Now, guess what? Your teacher's made that mistake once or twice in his life because nobody's perfect. But I always try to pay attention to make sure that I wasn't just rushing and I don't make that mistake happen. Okay, so why is this triangle a thing? Where's the proof of that? So down here, I'm going to draw a second triangle. And this is going to be, if I was a better artist, a triangle where all three of the angles are the same. So this is my choice. I'm making this triangle happen right now. Now I'm going to make another choice. If all of these angles are the same, that means all of these sides have to be the same. So what I could do is I could say this is 305, that makes this 305, and that makes this 305. But that's a very arbitrarily chosen number, so I'm not going to do it. Now what you might think is, well, you made an arbitrary side 1 before, let's do that again. That's a great idea, but I'm actually going to make it 2. So I'm going to make it a 2 instead of a 1, and I have a reason for that you're going to see in just a hot second. So all these angles match, so all the sides match. It's an equilateral triangle, that's what it's called. So here's what I'm going to do. I'm going to split this sucker in half exactly. And out of that one triangle, I'm going to create 2 triangles. This is why I made these numbers 2s instead of 1s. Because if I made those 2s, when I split this up, then this distance would be a half, and this distance would be a half. Now that's not wrong, it's just a little more annoying. Don't we like whole numbers over fractions? I know I do. So that's why I chose the 2s. I knew to do that ahead of time because it's not the first time I've done it. But if you made these 1s originally, then these would just be halves, and you'd go, oh, well, to avoid that, let me go back and make them 2s. Guess what? Been there, done that. All right, so if I split this perfectly in half, since this was 60 degrees, that means I now have a 30-degree angle here and a 30-degree angle here. This has to be right. And if this whole distance was 2, since we're splitting this exactly in half, that means that the distance from here to here has to be 1. The same for the other side. This distance would have to be 1 from here to here, from here to here. So now what I'm going to do is I'm going to make another triangle, but what I'm going to do is I'm going to extract it from this. So I had the one red triangle that I split in half to make 2 blue triangles, we'll say. Let's ignore the second one. Let's just use the first one. Does it matter which one? No. Let's use the right one. All these were pointed the other way, so let's use the right one. So I'm going to take this one. Again, I'm just taking what's right here, and I'm redrawing it by itself. So this distance was a 2. That hasn't changed. This is still a 2. This distance was half of the original distance across. It's a 1. which means this is an unknown. It's a b for now, which I'll erase in a bit, but you can solve that by, you guessed it, Pythagorean. So we can go 1 squared plus b squared is equal to 2 squared, which is 1 plus b squared equals 4. You can subtract 1 on both sides to get that b squared is equal to 3. So let me move up here. Take the square root of both sides. You're going to be doing this over and over and over throughout the course. And that says that b is the square root of 3. So that is why the 1, 2 square root of 3 triangle, it exists, and I didn't put the angles back in there, where this is 30 degrees, this is 60 degrees, and this is our right angle. That's the proof of this thing right here. That's why that triangle exists. Do you have to memorize this proof? No. Do you have to memorize these two triangles? You could argue no if you're a fan of that giant pain in the butt unit circle. I'm going to suggest that you try my way if you have done trigonometry before and didn't. If you hate it, then rely on the unit circle, but you have to learn one of those two methods or something in the universe that works as well. Okay, so why exactly is it that we have to memorize these? Because remember earlier how I said, oh, we don't know how to find the sine of 26 degrees without a calculator. We don't know how to find the cotangent of 81 degrees without a calculator. We don't know how to do the cosine of 3 pi over 11 without a calculator. You know what? Trigonometry existed before calculators. And people just had these giant, and I mean massive, tables of numbers for trig evaluations. So someone was literally measuring these things out for probably years, creating this table of values, and then you just looked it up. And the ones that are more popular, you probably memorized eventually. But we got calculators, so we don't have to do all that part. But there's still a lot of them by using the two triangles we just showed that we can actually get analytic answers without ever using a calculator. Because with 30 degrees, 60 degrees, 45 degrees, we can create right triangles out of them, and then we can use opposites, adjacents, and hypotenuses, hypoteni, to get their trig function evaluations. There's no nice fancy right triangle for the 22-degree angle or the 37-degree angle. There's only maybe one more good one of these in existence, and I'm not even going to introduce that in here because we won't ever use it, in fact. So these are critical for what we're about to do. Draw them 50 times, write them 50 times, say them 50 times, have someone else say them 50 times to you, however it is you learn. So now what we're going to do is we're going to establish, let's go off of my ridiculous font from my BRB. And again, thank you for your patience. I'm sorry I had to do that. But sometimes phone calls are phone calls. They can't be rescheduled. So let's discover what the basic trig function evaluations are for common angles. 30, 45, and 60 degrees. So for the sine of 45 degrees, we'll do the 45 first. Sine of 45 degrees. Now remember, SOHCAHTOA. Remember, we have the 1, 1 square root of 2 triangle for the 45, 45, 90. And then we have the 1, 2 square root of 3 triangle for the 30, 60, 90 triangle. Remember, 1 opposite the 30. That's critical. 2 is the hypotenuse there. 2 is the hypotenuse for both of these, but one of them is a radical, one of them is not. So sine of 45 degrees, that's SOH, opposite over hypotenuse. So the opposite over the hypotenuse, first of all, since it's 45 degrees, we're using this triangle. That's where our eye should be. And it's going to be easiest if we refer to ourselves from this bottom left angle, even though it's the same. You'll get the same answer. So from this one, this would be the opposite, this would be the adjacent, and this would be the hypotenuse. So sine is opposite over hypotenuse, so that's 1, this 1, over square root of 2. Now, this is a problem that we discussed last class. You don't get to have radicals in your answers. This is not acceptable. You have to rationalize the denominator, and that technique was to multiply top and bottom when it's a monomial by the square root in the bottom. If these are cube roots, the technique is different, but we don't really have that as an issue in here. So 1 times square root of 2 in the top is square root of 2. In the bottom, square root of 2 times square root of 2 is square root of 4. But the square root of 4 is 2. That's why we did this. We need this bottom to be a non-radical. It has to be a whole number. So the sine of 45 degrees is the square root of 2 over 2. Sometimes it's important to understand that it's also 1 over square root of 2. In fact, that's generally how I do it. And in fact, I don't memorize this at all. Like I said, I use this triangle. But if you were going to memorize it, understand that the memorization is 2 versions of it. You could memorize this one or this one. If you're memorizing this one, you got to clean it up. Again, this is us avoiding memorizing a unit circle. So the cosine of 45 degrees. Again, we're still here. Now we're going to do the adjacent over the hypotenuse. We're on Ca, C-A-H. This is the adjacent if we're using this as an angle. And that flip-flops if we use the other one. So adjacent over hypotenuse, that's 1 over square root of 2, which, guess what, is the exact same thing as before. So the work will be the exact same. I'm not going to reinvent the wheel. You do if you need to. Then let's do the tangent of 45. So again, using this triangle, TOA. Tangent is the opposite over the adjacent. The opposite is 1, the adjacent is 1, so that's going to be 1 over 1, which is 1. Like I said, some students memorize these, some students take my advice and use the triangles and SOHCAHTOA to put this together as a puzzle instead of just blatant memorization. Blatant memorization is great for classes like anatomy, but even still, if you know Latin, there's a lot tied in there. It's not just memorization anymore. It's actually, you can put some logic to some bones and things like that, which that's not my expertise, so I'm not going to pretend like it is. I just know those 2 little facts. All right, so there's our 45s. Let's go to the 30s. So the sine and cosine and tangent of 30 degrees. So we're on this triangle that I drew a little sloppy, but that's okay. You're not going to judge me for that, I hope. So 30 degrees, here's our angle, which makes the 1 the opposite, the square root of 3 the adjacent, and the 2 the hypotenuse. Again, I don't like that stuff being staying there permanently. You can do it that way in your notes, but not in mine. So sine of 30, SOHCAHTOA, S-O-H, opposite over hypotenuse. So the sine of 30 degrees is the opposite, which is 1, over the hypotenuse, which is 2. Awesomely enough, there's nothing else to do. The sine of 30 degrees is exactly a half, or 0.5 if you like decimals. So they're not all ugly radical numbers. These 2 are radicals, but the tangent of 45 was 1. The sine of 30 is a half. And don't just play a guessing game with this. And to figure out, hey, do I think it's going to be a radical or not? Do the work. Cosine of, I'm looking at the 45, sorry for that. Cosine of 30 degrees. So again, back to our 30, 60, 90 triangle. We're here. Opposite adjacent hypotenuse. So the adjacent's the square root of 3. We're on Ca. Adjacent over hypotenuse, square root of 3 over 2. So this would be the square root of 3 over 2. That's it. You don't have to clean this up because the bottom number is not a radical. This is perfect. It's fine. How about the tangent of 30 degrees? So going back up to our triangle. 1, 2, square root of 3. Again, 1 is the opposite, square root of 3 is the adjacent, 2 is the hypotenuse. Tangent of 30 degrees. Tangent is TOA, opposite over adjacent. The opposite is the 1, the adjacent's the square root of 3. So that's going to be 1 over square root of 3. That one does have a square root in the bottom, so we got to multiply top and bottom by square root of 3 over 3. Square root of 3 over square root of 3. which will give us the square root of 3 over the square root of 9, which is the square root of 3 over 3. And that's the answer. Now let's switch to the 60-degree angles. So the sine of 60. And I'm going to redraw them here for reasons. 45, 45, 90, degrees, 1, 1, square root of 2. When I'm starting out, I really like the angle I'm referencing to be this one. You can certainly do it from here. So from this, when you're talking about 60 degrees, the square root of 3 is the opposite. That's not a 0, that's an O. The 1 is the adjacent, and the 2 is the hypotenuse. See, it's not that the adjacent's always the bottom. It depends on what angle you're referencing from. So me personally, I know a lot of students mess up when they reference this way. So I'm going to redraw that thing. I'm going to redraw it with 60 degrees being that kind of anchor angle. So that's the wider one. Let's make it look something like that. So this will be our 60 degrees, which makes this the 30 degrees. There's our right angle. 30 degrees is supposed to be opposite the smallest number, which is 1. 60 degrees gets the square root of 3. 2 is opposite 90. Again, those are the largest numbers. So now the sine of 60 degrees, sine opposite over hypotenuse, opposite square root of 3, hypotenuse is 2. Square root of 3 over 2, and that's it. If I did it up here, I would have gone opposite of square root of 3 over 2. It would be the exact same thing. Notice something. Notice that this answer, the sine of 60 degrees, is the same as the cosine. I hate scrolling when I'm on draw. Is the same as the cosine of 30 degrees because they're cofunctions. 90 minus 30 is 60. They have the same answer. That right there helps show that cofunctions isn't just nonsense. All right, so the cosine of 60 degrees. So here, adjacent is 1, hypotenuse is 2. So the cosine of 60 is a half. The same thing as the sine of 30. 60 versus 30, those are cofunction angles. Sine versus cosine are cofunctions. Finally, we have the tangent of 60 degrees. Tangent is TOA, SOHCAHTOA, T-O-A, opposite over adjacent, square root of 3 over 1, which we do not need to clean up in terms of rationalization, but we do need to just write that not as a fraction for simplicity. You're going to do these 9 evaluations literally hundreds of times in this course. There is no exaggeration in my voice at all here. I use the word literally, not like from Parks and Rec. Sorry, silly there. But anyways, you will literally do these hundreds of times. That is not a joke. That is not exaggeration on the word. Or what's the fancy way of saying that? I'm not being hyperbolic, which we'll actually study hyperbolas later, which are not hyperbolic discussions. I have too much fun. Do this, then do it again, then do it again, then do it again, then do it again. Draw these triangles 50 times. Do these 9 evaluations 50 times. Whatever it is you have to do to get it stuck in your brain and ready to use over and over and over. And again, sure, you can blatantly memorize that sine of 45 is square root of 2 over 2. I never did it that way. I did exactly what you just saw me do. I took a triangle that has the information that I can extract for SOHCAHTOA, and then I did a rationalization because you have to. Not all of them have that rationalization. I only actually did it 2 times. Well, 3 if you argue about this one, but I shortcutted. Know which triangle you're supposed to use. Set the triangles up correctly. You're going to be mad at yourself on a test if you draw up these 2 triangles, but you swap the 30 and the 60, or you swap the 1 and the square root of 3. Every semester, I'm going to say at least one student, but it's a lot of students that do that. And maybe not for every problem, maybe just for some. So it's learn consistency, practice. Remember, how much time do I get out of you for homework every week? At least 6 hours. And Monday's a holiday, so you're probably going to be doing trigonometry for 8 or 10 hours that day, right? Right? Haha. Okay. Where am I going with this? Where am I going with this? Remember the title of this section was trig functions of any angle. Well, those were just 3 angles. What about if we were in quadrant 2, 3, or 4? So we can kind of open this up to any angle. Any angle outside of quadrant 1, we want to use something known as a reference angle. Evaluate trig functions. What is a reference angle? I'm glad you asked. A reference angle is the angle from the closest. I'm going to all caps that and underline it actually, or bold it. Let's bold it in all caps it. Closest x-axis, terminal side of your angle. So we said that when we're talking about angles, our initial side is supposed to be the positive x-axis, and the terminal side is wherever that angle forces us to be. And we drew up dozens and dozens of those in previous classes. But in order to use that 30, 60, 90, or 45, 45, 90 triangle when we're outside of a quadrant, outside of quadrant 1, I mean, what we can do is use a reference angle. We can actually turn something like 120 degrees into 60 degrees as a reference angle. Or we could turn 91 degrees into 89 degrees as a reference angle. And there are reasons for this that we're going to study over the next couple of classes. I don't want to give you too much of a kind of a proof for this for now. So let's take a little leap of faith with me, and we'll start seeing why this actually works over time. So all of the trig functions, again, leap of faith for now, all of the trig functions be identical for the original angle and its reference angle, which looks like this. You still have the same theta, but you give it a little 1 as an exponent. It's not actually a 1, it's not actually an exponent, it's just notation. So when you see that, it's known as a prime. So that's called theta prime. That's a reference angle. That's the terminology and notation that we use for a reference angle. So an angle and its reference angle will have the exact same trig function outputs, except for a potential sign, SIGN sign change. So for any angle outside of quadrant 1, we are going to want to use a reference angle. If you're not just going to blatantly memorize a unit circle, we're going to want to use a reference angle. So we're going to take an angle that was in quadrant, say, 3, and make a reference angle that would go in quadrant 1. Because when we're in quadrant 3, we can't really make a right triangle out of the angle from the positive x-axis. So we want to be able to create a right triangle, which means we're stuck to less than 90 degrees. But the beauty is, besides maybe a change in the plus or minus sign of the answer, the sign of a regular angle, SIN, sine, will be the same thing as the sign of its reference angle, except maybe negative. The tangent of an angle will be the same as the tangent of its reference angle, except maybe negative. The cosecant of an angle will be the same as the cosecant of the reference angle, except maybe plus or minus difference. So here's kind of the idea here. If we have a regular Cartesian coordinate system, here's our x-axis, here's our y-axis, and I'm going to draw it in the first quadrant for this one, but let's say that our angle formed is right here. Here's our terminal side. Now this point we'll call P, it has coordinates x and y. So here's our traditional angle. And let me just kind of form a right triangle out of this. So even though the angle itself doesn't say make a right triangle, this is what we like to do. We like to form a little right triangle out of it, like so. So if that coordinate is x comma y, the distance along the horizontal part is that x value, and the distance along the vertical part has to be the y value, because you have to go right and up, right based on the x number, up based on the y number. So for this angle, if that's your angle, the opposite is y, the adjacent is x, and then the hypotenuse, because we're generally going to talk about this thing in relation to a circle, we label as the letter r. So that your 6 trig functions are just sine of theta would be the y value over the radius. The cosine of the angle would be the x value of the radius. The tangent of the value would be opposite over adjacent, y over x. See, I'm just giving these different names. Instead of calling them opposite, adjacent, hypotenuse, I'm giving them names that are related to their points, x, y, and r. Or we can do the other 3. Cosecant would be r over y, just flipping the sign. Secant would be flipping the cosine, which is r over x. And then cotangent would be x over y. So this is going to be important, especially for what we call the quadrantal angles. But it also helps us establish this whole, everything's the same for an angle versus reference angle, except maybe a plus or minus aspect and sign change. So now I'm going to draw this thing not being in quadrant 1. So that was just to establish the blue stuff over there. Now let's do an angle that's over here. So here's our theta. Here's the lengths if we want to make a right triangle out of this. This length would be our opposite. This length would be our adjacent. For the point itself, this point right here, let's give it, instead of giving it x and y, let's call it a and b. And hold on, I need a little more cleanliness there. A and b, and I need a little more space too. A comma b, because I'm going to change something about this in just a second. So this point right here, if I call that a and b, that means that this height is a, which means this distance is a. Incorrect. Sorry, I'm rushing in my head. Not rushing, but I'm moving ahead in my head. That's not the a. If that height, that's the height, that's the b. That value should be b. And then initially, I'm going to call this over here a, but that feels weird to call it a because it's negative. Now, it's fine. We could just say, okay, a could be positive or negative. But I want to have this labeled as a as well. So let's instead make this a negative a. Do we see why I'm calling that a negative and then b a positive? But I'm doing that so that I can just label these sides as a and b. So in the right triangle, there's no positives or negatives. But in terms of actual coordinates, because we're going left, that makes this a negative value. So this point right here is negative a comma b. So here is the, I'm sorry, where I put theta, I'm also doing that wrong. That wasn't theta. This is the theta. The actual angle is swinging over here. Inside, this would be our reference angle, theta prime. So I'm going to do this with red so it screams out. So that's our reference angle. A reference angle is us taking an original angle and making it something inside of a right triangle, something less than 90. And spoiler alert, it's going to end up typically looking like this when you draw it out. And we'll talk about how to mathematically calculate these after. Okay, so if this is your regular angle, so we're going more than 90 degrees, maybe 120 degrees, maybe 132 degrees, something like that. This angle would have to be its supplement to make sure that they form a straight line. We discussed that last class, that two supplemental angles add to 180. So if this was 120, that would make this other one 60 because 180 minus 120 would be 60 degrees. So let's take this triangle and let's draw it again. And I'm going to do it with orange to make it scream out. But I'm going to draw out the reference triangle with the reference angle in quadrant 1. That's a little too steep, or actually not steep enough technically. I'm trying to do as best as I can here. So now this little angle right here is going to be theta prime. And it's going to have sides over here and here. Now, these are very, very symmetric. Symmetry is the name of the game. So if this vertical distance is B, this vertical distance is B. If this horizontal distance is A, this horizontal distance is A. It's basically just reflecting it across the y-axis. When you reflect something across a y-axis, the point just changes in x value. So the point is now A comma B. And it is this idea that makes all of those trig functions the same, except in terms of SIGN sine. Because the right triangles I just drew up mimic each other, it's just for the original one, that was supposed to be a negative for the x value. Over here, it's a positive. So if you use this version of it, you just got to remember to put a negative in the answer when you were in quadrant 2 or 3 or 4, depending on the trig function. So I just threw a lot at you that probably doesn't make a lot of sense at first, but after we do this 100 times, it starts to really sink in after you see these evaluations come through. But again, the main point of this little drawing detail was to say, all trig functions will be identical for an angle and its reference angle, except for a potential sign change, and that's because of these coordinates basically changing SIGN sometimes. And these coordinates tie in to the sine, cosine, tangent, secant, cosecant, and cotangents. So if a coordinate changes sine, that means its trig function changes sine. So let's give you a mnemonic device to help you. A, S, T, C. This stands for a smart trig class, which is what we have right here. Kind of like FOIL, in that FOIL helps us remember first, outer, inner, last for multiplying binomials together. It's kind of like PEMDAS, please excuse my dear Aunt Sally, to remember the order of operations. It's kind of like SOHCAHTOA, some old horse got another horse taking notes away, to help us remember sine is opposite over hypotenuse, etc., etc. So what does this really stand for? All sine, S-I-N, tan, and then cosine. That's what it stands for. All sine, tan, cosine. What this does for us, this describes which trig functions out of the 3 primary, sine, cosine, and tangent, are positive in which quadrant. So in quadrant 1, they're all positive. Quadrant 2, it's only the sine that's positive. Quadrant 3, it's only the tangent that's positive. Quadrant 4, it's only the cosine that's positive. I don't want to abbreviate positive. Notice I switched from Roman numerals to regular old numbers. I actually did that on purpose because I don't care. In my math lab, they will probably specify which one you'll need to answer, but it's very rare you're answering a quadrant as part of a homework question. Why exactly is this? Let's draw up another one of these. And I'm going to label in each quadrant the sign, the positive or negative sign of the x-coordinate, the y-coordinate, and the ratio of the two. But specifically y over x, because that's going to relate to tangent. All right, so if you're in quadrant 1, an x-coordinate has to be positive. If you're in quadrant 1, a y-coordinate has to be positive because you go right or up, or right and up. And the division of a positive and a positive is a positive. If you're in quadrant 2, your x is negative because you've got to go left, but you're still going up, so your y is positive. And if you divide a positive and a negative, you get a negative. In quadrant 3, you're going left and down, so your x and y coordinates are both negative. However, the ratio of them is positive. If you're in quadrant 4, you're going right and down, which means your x is positive because you're going right. Your y is negative because you're going down, and the ratio of them would be negative. A negative divided positive is a negative. Why did I do this? I'll come back to it in a second. Because all of your sines and cosines and tangents are essentially based on the x's and the y's. You might say, well, Mr. Beckner, you didn't talk about the r's. R is the radius of a circle. It's always positive. We're not considering a coordinate for the radius. That's just an intrinsic value. So x divided by r is positive, it won't be affected. Y divided by r, it's not affected because it's positive. So since sine essentially goes like x, this is like a tilde, a curly equal sign, but only one of them. This says sine goes like y. I wrote x because I was looking at an x. I keep doing things like that today, I'm sorry. Sine is essentially the y coordinate. It picks up the plus or minus aspect of the y coordinate. Cosine picks up the plus or minus aspect of the x coordinate. Tangent was opposite over adjacent. Opposite over adjacent is y over x. So tangent picks up the plus or minus aspect of the ratio of those two. So because when you go right, x is positive, that says your sine is positive in quadrant 1, and it's positive in quadrant 4. But to go left, that makes it negative, so your sine is negative in quadrant 2 and in quadrant 3. Your y value is whether you're going up or down. You're going up in quadrant 1 and 2, so you're I keep doing that. I keep saying sine instead of cosine. X's are cosines. And I know why. It's because I usually write y and then x on this. That's what screwed me up here. X goes like cosine. See, x goes like cosine. That was my bad. So cosine positive, cosine negative, cosine negative, cosine positive. Y's are heavily related to the sine, the S-I-N. So we're going up, positive. We're going up, positive. We're going down, negative, down, negative. Left and right is cosine or x. Up and down is sine or y. Tangent is the ratio of the two. Everything I filled out is right here in ASTC. All of them are positive in quadrant 1. So here's your all, here's your A, all. There's your all. They're all positive. Why did that get weird? They're all positive in quadrant 1. In quadrant 2, it is only the sine that is positive. Look at that. Cosine and tangent are negative, sine is positive. So it's only the sine that's positive. In quadrant 3, it's tangent that's positive only. Negative, negative, yep, tangent's positive. And in quadrant 4, it's cosine is the only one that's positive. And sure enough, cosine's the only one that's positive. So here's what you can do as students. You can recreate this, and you don't have to do it with as much detail. Remember that sine goes like y, cosine goes like x, tangent goes like y over x. Spoilers, you will need to memorize this ultimately anyways. This will keep coming back to haunt us. But if you don't just want to blatantly memorize or have to recreate this diagram every time to remember in which quadrant sine's positive and which quadrant it's negative, that kind of thing, this ASTC gets all of that a lot quicker. So you know if your angle is in quadrant 2, if you're doing a sine, it's going to be positive. If you're doing a cosine, it's going to be negative. If you're doing a tangent, it's going to be a negative. But Mr. Beckner, what about the other 3 trig functions? What about secant, cosecant, and cotangent? How do I know whether they're plus or minuses? Because reciprocal relationships share the same plus or minus. So if the sine is positive, that means the cosecant is positive. If the cotangent's negative, that means the tangent's negative. They go hand in hand. So for cosecant, secant, and cotangent, just use reciprocal identities. Plus or minus aspects. Same for recips. And unfortunately, on that bombshell, we're going to have to cut class because it is time. We're not going to get to any examples of this. So we have not finished 5.3. We still have a decent amount of work to do with 5.3, maybe half the section, a little less than half since we at least got all this done. But I've given you several approaches for several things. I love being able to do that because some of you are going to use one approach and some of you are going to use another. Are the way I do things, or the 2 ways I introduce, the only ways? No, there's probably a 3rd, 4th, 5th, 17th way to do things. If you can go to the internet and find them, or a tutor and find them, if they work, as long as it always works for you and you don't forget them, that's fine. Just don't ask me about those methods because it could be something I've never seen. I haven't seen every method in the world. And I'm not going to recreate a whole method because we just don't have enough time. Barely have enough time for my mini rants. All right, so please make sure you complete that homework for 7.2. The due date should be 7.1 and 7.2. We just finished 7.2 today. Now, I know that a week from today, no, I'm sorry, a week from Monday was the holiday. Never mind. I got myself confused. So the 2nd section, 2nd section, I mean, 5.2, we do September 9th. There we go. So if that's not set up in my math lab, I'm going to go correct that in just a second. So have a good one. Please study this. Please rewatch it. Please go ahead and try practicing the homework for 5.3, whatever you can. But like I said, we still have a lot to do that we'll cover in a week because Monday's a holiday. So enjoy your day off. Study some time if you can. But until Wednesday, take it easy.
Mr. Beckner?
Oh, sure. Go ahead.
I have a question. Are you going to do the converting decimal degrees to minutes and seconds?
You know what? I do need to cover one of those as an example, but I will openly admit I am not going to test on that. And that's why this is actually not the first time in a trig class I forgot to give that.
Oh, okay.
So thank you for bringing that up. If someone will actually remind me at the top of class on Wednesday, that'll be the first thing we'll do, and then we'll get back into 5.3. Thank you very much.
Gotcha. No problem.
All right, y'all take care.
All right.